So imagine you are the captain of like a massive, multi-billion-dollar cargo ship.
Okay, I'm picturing it.
Right. And it is the size of a skyscraper. It takes actual miles just to turn. And it requires this unbelievable amount of fuel just to change direction even a little bit.
Yeah, massive inertia.
Exactly. Now imagine someone hands you a single, tiny, specialized steering wheel bolt. And they look at you and say, hey, if you just swap out this one little bolt, this entire massive ship will suddenly know how to perfectly navigate the canals of finesse.
You would think they were completely out of their mind.
Right. It sounds insane. But tonight, we're looking at a mathematical trick that does, well, exactly that to large language models.
It really does. It's wild.
I mean, it takes a 140 gigabyte artificial brain and completely rewires its behavior with a file that is literally smaller than an MP3.
It is a complete structural paradigm shift.
Yeah.
We're talking about taking something that used to require massive server farms and shrinking the workload so drastically that you can do it on consumer hardware.
Which is huge. Welcome to the Deep Dive, by the way. I'm your host, the resident software engineer trying to keep up with all this. And sitting across the mic is our AI architecture expert.
Hey there. Glad to be here for this one because it's a game changer.
It really is. And if you are listening to this right now, you know exactly why that matters. It's late. The screen is glowing. You are probably staring at a terminal window right now, maybe nursing a lukewarm coffee.
Or a very strong energy drink.
Yeah. Exactly. And you're just thinking about how to integrate an LLM into your company's application. You're a software engineer, but suddenly overnight, your product manager expects you to be this, like, AI wrangler.
The whole tech stack just shifted out from under people.
Right. You're trying to figure out how to make these massive, unwieldy neural networks output perfectly formatted code or speak in your specific brand voice.
Mm-hmm.
And you have to do it without burning through your entire cloud budget in a single afternoon.
Which is a very real risk.
Oh, absolutely. So tonight, we are going strictly into the weeds on the concept that is completely rewriting the rules of AI development for you. We are exploring LoRA, low-rank adaptation.
And, to really grasp why LoRA is so revolutionary, we kind of have to look at the nightmare it replaced.
The dark ages of, what, a year ago?
Pretty much. But before this technique, if you wanted to fine-tune an LLM to teach it a new trick or adapt it to your specific code base, you had to do a full fine-tuning.
Right, the brute force approach.
Exactly. That meant updating billions of parameters, billions of floating point numbers across a massive neural network, all had to be recalculated, adjusted, and saved.
Just a ridiculous amount of compute.
It was incredibly heavy brute force lifting.
Right, which meant fine-tuning was essentially a playground exclusively for the massive tech giants. I mean, if you didn't have a warehouse full of GPUs, you're just stuck using off-the-shelf models that didn't quite do what you needed.
Exactly, you were locked out. But LoRA bypasses all that brute force. And, well, my core belief here is that the absolute best engineering solutions, the ones that actually change the industry, rarely come from just throwing more hardware at a problem.
Yeah, you can't just scale your way out of everything.
Right. The real breakthroughs come from recognizing fundamental mathematical efficiencies. And LoRA works smarter at the algorithmic level.
Okay, so let's unpack this. Let's get into the mechanics of that efficiency, because I hear LoRA thrown around on engineering subreddits literally constantly.
Oh, yeah, it's everywhere.
People treat it like it's actual magic. But there is a very specific matrix hack at the center of this, right?
Yeah.
The foundational idea relies on an empirical observation made by researchers.
Yes, that is the starting point.
They noticed that when you fine-tune a model, the necessary weight changes are, quote, low rank. So translate that for a developer who hasn't taken a linear algebra class in a decade. What does low rank actually mean when we pop the hood?
Well, think about the pre-trained LLM as an incredibly complex, highly educated system. It already knows grammar, syntax, logic, and general facts about the world.
Okay.
And it stores all of this in billions of parameters, which are essentially just giant grids of numbers, matrices.
Right. Big Excel spreadsheets in the sky.
Basically, yeah. So when you fine-tune this model to do a new specific task, you don't actually need to rewrite all of its core knowledge. I mean, it doesn't forget English just because you're teaching it to output Python.
Right. The foundation's already poured. The house is built.
Precisely. So the empirical observation that researchers made is that the actual changes required to adapt that model to a new task, they don't require the full massive complexity of the original matrices.
Wait, so the updates themselves are simpler than the original data?
Yes, the necessary updates can be represented in a much lower dimension. That's what they mean when they say they are low rank. It basically means the updates are highly correlated. You just don't need a massive grid of independent variables to capture the new behavior.
Okay, let me try to put this in traditional software engineering terms.
Go for it.
Instead of rewriting and recompiling the entire monolithic code base every single time we want to add a feature, LoRa is like writing a tiny targeted patch file.
That is exactly it.
We leave the main code base locked, totally read-only, and this little patch file just hooks in and overrides the specific functions we need at runtime.
That is an excellent way to conceptualize it. You freeze the original massive neural network. You literally don't touch those base weights at all during training.
So no risk of breaking the core intelligence.
Right. Instead, you track the updates to those weights as a completely separate entity. And because of that low-rank observation we talked about, you don't need a massive matrix to store those updates.
Because they're highly correlated.
Exactly. You can represent those billions of parameter updates mathematically by multiplying two much smaller matrices together. Let's just call them matrix A and matrix B.
Wait, hold on. This is where the math sounds completely too good to be true.
It always does the first time you hear it.
I mean, you're telling me we can take an update matrix that is supposed to hold billions of values and just slice it into two smaller matrices? How does multiplying A and B actually achieve the extreme compression we are seeing here?
It's all in the geometry.
Because in practice, I'm seeing training footprints shrink down to 0.1%, maybe 1% of the total model size. That's absurd. Walk me through the actual numbers.
Sure, let's visualize the sheer elegance of this compression. Imagine one single layer of the original base model has a weight matrix that is 10,000 by 10,000.
Okay, 10,000 by 10,000, that's 100 million parameters.
Right. If you were doing full fine-tuning, you would have to calculate and keep track of 100 million parameters in memory just for that one single layer.
Which is exactly why my local GPU immediately runs out of memory and crashes.
Exactly. It's an enormous memory bottleneck. But with LoRa, we use what's called a rank.
Okay.
And you can think of a rank as a hyper-compressed bottleneck dimension. In practice, engineers usually set this rank somewhere between 8 and 64.
Let's use 8 for this example, just to keep the math easy.
Perfect. So instead of training one massive 10,000 by 10,000 matrix, we create two new ones. Matrix A is 10,000 by 8.
Okay.
Matrix B is 8 by 10,000.
Ah. Okay, I see the geometry here. I'm picturing it.
Right.
Matrix A basically compresses the 10,000 inputs down into just 8 dimensions. It forces all that information through a tiny pipe.
A tiny little bottleneck.
And then Matrix B takes those 8 dimensions and projects them back out to 10,000 on the other side.
Right. And when you mathematically multiply a 10K by 8 matrix with an 8 by 10K matrix, the result is, well, it's a 10,000 by 10,000 matrix.
Wait, so you still get the massive grid of updates to apply to the base model at the end?
Yes. But think about how many parameters you actually had to keep in memory and train to get there.
Oh, man. Let's do the math.
Yeah.
Matrix A has 10,000 times 8, so 80,000.
Yeah.
And Matrix D is another 80,000. That's 160,000 parameters total.
Down from 100 million.
Down from 100 million. That is absolutely staggering. That is the 0.1% reality right there.
That's incredible, isn't it?
It is. But wait, let me play devil's advocate here. If I'm bottlenecking 100 million potential data points through just 8 dimensions, I mean, I have to be losing data, right?
You are.
It's like taking a raw 4K photograph, compressing it into a heavily artifacted JPEG, and then trying to blow it back up to a billboard size. You lose the fine pixel details.
You do lose the microscopic details. But in this context, for fine-tuning an LLM, that is actually a feature, not a bug.
Wait, really? How is losing data a feature?
By forcing the training data through that tiny rank 8 bottleneck, the math inherently prevents the model from memorizing random noise in your training data.
Oh, it acts as a regularizer.
Exactly. It only has the mathematical capacity to learn the most important high-impact directional changes. It learns the broad strokes of the behavior you want, which is usually exactly what you need for generalization.
Okay, that is a brilliant mechanism. You are isolating the delta, the actual behavioral shift, and geometrically forcing it to be efficient.
Precisely.
But let's be real for a second. As a developer, I know that extreme optimization always comes with a massive catch. There are no free lunches in software architecture.
Definitely not.
You cannot delete 99.9% of your trainable parameters and get the exact same outcome in every situation.
You are absolutely right to be skeptical. There is a catch, and the trade-off here is a classic tension between raw efficiency and deep foundational knowledge.
So where does it actually break?
Mm.
Because the data shows that LoRa achieves 90 to 97% of full fine-tuning performance for most practical tasks.
Which sounds great on paper.
Right. And if I go to my product manager and say, hey, the new AI feature is 97% compatible, they might just sign off on it immediately.
They probably would.
But as the engineer actually deploying it, I'm lying awake at night worrying about that missing 3%. When does that 3% gap actually cause the application to fail?
It fails when you misunderstand what the bottleneck is capable of holding. The performance gap becomes a massive issue for tasks requiring deep knowledge acquisition or radical behavioral shifts.
Deep knowledge acquisition. Okay, give me a concrete scenario. What are we asking the model to do that it simply can't handle with LoRa?
Let's say you are building an AI assistant for a highly specialized pharmaceutical firm, or maybe a really niche legal practice.
Okay.
You want this model to ingest, fully understand, and flawlessly recall thousands of pages of entirely new proprietary research, stuff that never existed in its original training data.
So you were asking the model to learn completely new foundational facts about the world.
Exactly. And if you try to do that with LoRa,
Let me guess it fails.
it will fail, or worse, it will hallucinate wildly. Because there simply isn't enough memory capacity in that tiny 1% of trainable parameters to store vast amounts of brand new factual information.
Ah, right. The bottleneck is too tight.
Yeah, you are trying to pour an entire ocean of new facts into a thimble. That rank 8 bottleneck we talked about. It's a thimble, it won't fit.
That makes a ton of sense.
For that kind of radical knowledge injection, you often have no choice but to do a full fine-tuning. You have to physically rewire the billions of base parameters so
Right.
the model has the actual physical capacity to store the new data.
Okay, the thimble overflows. I love that analogy.
Yeah.
So what is the 90 to 97% where this thimble is actually the perfect tool?
Well, LoRa excels incredibly well at teaching the model how to behave or how to format the knowledge it already possesses.
Format over facts.
Right. For instance, if you want a model that already understands general programming to specifically output code in your company's proprietary, highly structured style guide.
Oh, nice. LoRa would be brilliant for that.
It is.
Or let's say if I'm building a back-end service and I need a natural language model to reliably 100% of the time output its responses in perfectly formatted JSON so my API can parse it without crashing.
Exactly. Because you aren't teaching it new facts about the world. You're teaching it form, tone, and format.
So it's basically taking its existing genius and giving it a new uniform to wear.
Exactly. If you want a customer service bot that adopts a very specific, quirky brand voice, LoRa hits that 97% performance mark effortlessly. You are just steering its existing intelligence into a highly specific lane.
Form versus substance. Formatting versus foundational facts. Okay? So if you just need to steer the ship, you swap out the steering bolt, you use LoRa.
Right.
But if you need to completely rebuild the engine to run on a totally different fuel, you have to do the heavy lifting of full fine-tuning.
That is the exact mental model developers need to adopt. And frankly, for the vast majority of software applications being built by independent teams right now, they just need to steer the ship.
Yeah, most of us aren't training a model from scratch to cure disease.
Exactly.
Yeah.
They are taking off the shelf generalized intelligence and just wrapping it in an application layer format.
Which leads us directly to the most critical part of this entire discussion, shipping to production.
Ah, yes. The real test.
Because, okay, the math saves us during training. My local GPU didn't melt, which is great.
Always a plus.
But training is only half the battle. If I have to load this fine-tuned model into AWS or Azure to serve live user traffic, am I still paying to host a massive neural network? I mean, how does this A times B matrix hack actually run in a production environment?
This is where the engineering choices get incredibly strategic.
Yeah.
Because your deployment architecture completely changes based on how you handle these adapters.
Okay, break it down for me.
There are two primary paths. You can either merge the LoRa adapters permanently into the base model, or you can keep them completely separate for multitask serving.
So let's tackle merging first, because that seems to be the default for maximum performance. If we merge the adapters, it's often described as zero overhead inference.
Yes, that's the industry term for it.
So let's stick with our development analogies. Merging feels a lot like statically compiling a binary.
Oh, that's a perfect comparison.
Like you take all your dependencies, all your libraries, and you just bake everything into one single, highly optimized executable file for maximum runtime speed.
It is exactly like statically compiling.
Yeah.
If you are building a real-time application where latency is the ultimate metric, say, a live voice transcription, every single millisecond counts.
Right. Users hate waiting.
They do. So when you merge a LoRa adapter, you run that A times B matrix multiplication one final time. You expand those 160,000 parameters back out into the full 10,000 by 10,000 grid.
Okay.
And then you simply perform addition. You permanently add those updated weights directly into the base model's weights.
You literally fuse them together mathematically.
You fuse them. So
Yeah.
the inference engine, the software actually running the model in production, doesn't even know LoRa was ever involved.
It's amazing. As far as the server is concerned, it's just running a standard single set of weights.
Correct. There is zero latency penalty to check a secondary file. Zero computational overhead. The runtime speed is identical to running the raw, untouched base model.
Okay, but let me push back on that for a second.
Okay.
If merging is so incredibly fast and has absolute zero overhead, why would a team ever choose the alternative? Why keep the adapters separate?
Cost. Pure, brutal cloud costs.
Because in my developer brain, keeping them separate sounds like dynamically loading DLLs or routing traffic to microservices on the fly. It introduces an extra step, which inherently means it's slower. Why would you ever willingly take the latency hit?
You take the latency hit because of the terrifying reality of VRAM costs. Think about the resource constraints of serving LLMs at scale.
So cheap.
It's incredibly expensive. A 70 billion parameter base model might require 140 gigabytes of VRAM just to load into the GPU so it can start thinking.
Wow. 140 gigs?
And 140 gigabytes of high bandwidth GPU memory is astronomically expensive to rent in the cloud by the hour.
Right. You're renting specialized hardware. It adds up fast.
Now imagine you are the lead engineer for a multi-tenant SaaS application. Let's say you have 100 different enterprise customers.
Okay.
And you've done the right thing. You've trained a specific, highly tailored LoRa adapter for each one of those 100 customers so the AI perfectly matches their specific corporate tone and guidelines.
Oh, man, I see the math problem now.
Phew!
Yeah. If I statically compile, if I merged every single one of those adapters, I would be creating 100 completely unique 70 billion parameter models.
Yes. You would need to load 100 different giant models into memory.
That's 100 times 140 gigabytes.
Yep. You would need 14,000 gigabytes of VRAM just to keep your application online and ready for traffic.
The cloud hosting costs would literally bankrupt your startup before you even launched.
Exactly. It is physically unscalable. So by keeping the adapters separate...
I only load that massive 140 gigabyte base model into VRAM once.
Yes. Just one instance of the heavy lifting. You load the massive frozen base model once. And because those individual LoRa adapters are so incredibly small, maybe 50 to 100 megabytes each, you can hold hundreds of them in standard system memory effortlessly.
So how does the routing actually work at runtime then?
Well, when an API request comes in from customer A, the system routes the prompt through the single massive base model, but dynamically applies customer A's 50 megabyte adapter matrices on the fly.
Just injecting the math right at runtime.
Exactly. And a millisecond later, customer B sends a request. The system uses the exact same base model, but seamlessly swaps in customer B's adapter instead.
That is multitask serving. One massive foundational brain supporting dozens or hundreds of specialized personalities simultaneously.
That's the beauty of it.
You sacrifice a tiny, almost microscopic amount of computational latency to calculate those dynamic weights, but you save hundreds of thousands of dollars in infrastructure costs.
It is literally the difference between a business model that is viable and one that is physically impossible to fund.
That's wild.
That architectural flexibility, the choice between static merging for raw speed or dynamic multi-serving for scale, is what elevates LoRa from just a neat math trick to an industry-defining engineering tool.
And really, the ripple effects of this tool are completely reshaping the tech landscape, because it's not just about one company optimizing their AWS build.
It's way bigger than that.
This specific mathematical efficiency has catalyzed an entirely new developer ecosystem. Like, we are seeing the rise of things like PEFT.
Parameter-efficient fine-tuning.
Right, PEFT frameworks and these adapter hubs. And When I look at how an adapter hub functions, I immediately think of NPM for Node.js or pip for Python.
Because that is exactly what they are becoming. They are repositories of behavior.
Right. If I'm building an app today and I need a library to parse dates, I don't write it from scratch. I just type npm install moment, and I move on with my life.
Exactly.
We are rapidly moving toward a reality where if I need my LM to perfectly understand complex SQL queries, I don't train it from scratch.
No.
I just go to an AI adapter hub. I find a 50 megabyte LoRa adapter that some brilliant engineer in Berlin already trained. I download it, and I dynamically slot it into my base model.
You are describing the true democratization of artificial intelligence. I mean, for the first 2 years of the generative AI boom, the narrative was that only massive corporations with football fields of server racks could play in this space.
Yeah, the cost of entry was a moat that no indie developer could ever cross.
But the LoRa ecosystem has completely shattered that moat. Solo developers are pulling down massive open source models, loading them onto consumer-grade gaming GPUs in their bedrooms, and training custom AI behaviors over a weekend.
It's honestly incredible.
It is. Tools like the PEFT library have standardized how we apply these techniques. You don't need a PhD in machine learning to use them anymore. You just need to understand the basic software architecture of how to load a model and apply an adapter.
It puts state-of-the-art capability directly into the hands of the open source community.
And what's wild is that the efficiency push isn't stopping here.
Oh, I know. In our next deep dive for this fine-tuning module, we're going to explore the next evolution of this, which is QLoRA.
QLoRA is a phenomenal advancement. If LoRa is about radically reducing the number of parameters you have to train, QLoRA introduces quantization.
Which shrinks the actual data type size.
Exactly. It compresses the actual mathematical precision of the base model's memory footprint, shrinking the VRAM requirements even further without breaking the model's logic.
It's the natural next step in making these massive models run on smaller and smaller devices. I cannot wait to get into the math on that one.
It's going to be a fun one.
But to bring our focus back to what we've unpacked tonight, we started with the sheer elegance of the matrix hack.
Taking an impossible 100 million parameter update, forcing it through a tiny rank 8 bottleneck, and doing the job with just 160,000 parameters.
We established that extreme efficiency is really the foundation of modern AI development.
We tackled the trade-offs too. The reality that you can get 97% of the performance, which is perfect for teaching a model form, formatting, and tone.
But acknowledging that you can't pour an ocean of brand new facts into a thimble.
The crucial engineering distinction between steering the ship and rebuilding the engine entirely.
Yeah, that distinction is everything. And finally, we explored the very real production architectures, the fork in the road every developer hits at deployment.
Merging the adapter for statically compiled zero latency speed versus leveraging dynamic multitask serving to save a fortune on VRAM while hosting hundreds of specific AI personalities.
Which ultimately plugs every single developer into a rapidly expanding modular open source ecosystem.
It's a great time to be building.
It really is. So if you are a software engineer listening right now, the takeaway is pretty clear. The barrier to entry is gone. You do not need a supercomputer to mold these models to your will. You just need to understand the architecture, grab an adapter, and start building.
But if we zoom out for a second and look at the trajectory of this industry, this modular approach leaves us with a profound question about the future.
I love these big picture questions. Lay it on us.
If base models become massive, frozen commodities, just foundational utility layers provided by a few giant companies, and all the specific, highly valuable behavior, the unique business logic, is contained in these tiny, easily swappable 1% LoRa adapters.
Yeah.
How does that change the way we think about intellectual property?
Oh, wow.
I mean, when the massive brain is public, but the tiny steering wheel is proprietary, where does the real value in software engineering actually live tomorrow?
That is a phenomenal question, and definitely one worth taking to the whiteboard. Think about where your value lies in the stack. Keep building, keep questioning. We will catch you on the next deep dive.